This is lesson 4.3, and today we're going to be talking about rotations. So some important background knowledge for rotations. They can go in either the clockwise direction, which means it follows the hands of a clock, or counterclockwise, which would be going the opposite ways the hands of a clock would go. One turn on your graph would be 90 degrees. Then two turns would be 90 and 90, or 180 degrees. And then three turns would be 90, 90, and 90, or 270 degrees. And we know then a full circle is 360. So a rotation is a turn around a fixed point called the center of rotation. And the figure is going to rotate at a specific angle and direction. So that's our counterclockwise or clockwise, and our 90, 180, or 270. It could be any angle, but we're going to focus on those three. So though the figure can rotate around any fixed point, the most common center of rotation is the origin. All right, and here we have a picture down here of a 40-degree counterclockwise angle at center P of figure QR to Q prime R prime. All right, so like we just said, it shows a 40-degree counterclockwise rotation. So rotations can be clockwise or counterclockwise. But what's important is all of them are counterclockwise unless otherwise noted. So they have to tell you if it's going to be clockwise. If they don't tell you a direction, we are to assume it is counterclockwise. And I'm just usually going to abbreviate counterclockwise to CCW and clockwise to CW because those are pretty long words. So if I ever have to write it out, I'm going to abbreviate. So if I had my original triangle EFG and I did a 90-degree rotation about the origin, I would get the points 1, 2, negative 4, 1, and negative 1, 5, 3, 4. 1, 2, 3, 4, 5. Oh, because that's not 1, 2. That's why it looks weird. That was 1, negative 2. 1, 2 is there. Okay. And this was E prime, F prime, and G prime. So what I really could have done is I could have taken this original triangle with the origin, and I could turn it one click, right, 90 degrees counterclockwise, and making sure my origin is still at the origin, that's where my picture should end up. So what happened to the x values of all the points? So the x values were originally 2, 1, 5, but now they're over here, 2, 1, 5. So what happened was they switched with the y values. And then the y values were negative 1, 4, and 1, and now I have positive 1, negative 4, and negative 1. So not only did they switch with the x's, but they also changed sign. So what that would look like is every point that started as xy switched places, and then the first spot changed its sign. So there's actually 3 rules, one for 90, one for 180, one for 270 when we rotate around the origin. So our rule for 90 degrees counterclockwise, we just said, is negative yx. Our rule for 180 is actually negative x, negative y. So both of them change their signs from whatever sign they were to the opposite. And then 270 is y, negative x. So it's similar to 90. They switch signs, but now instead of the first spot becoming the opposite sign, the last spot became the opposite sign. And I remember that because 90 comes first, so I do the first spot. 270 comes last, so I do the last spot. So let's try this problem. We want a graph triangle ABC with these points and its image after a rotation 90 degrees about the origin. So anytime I'm going to do a transformation, I'm going to write my rule first. So I know for 90 degrees, it's going to be negative y x. The way I apply that rule is I'm going to take my 2, 7, I'm going to switch them first, and then I'm going to change the sign of the first position. All right, so for B prime, I'm going to switch them first, and then change the sign of the first position, and then the same thing for C prime. Change them first, switch them first, change the sign of the first position. So this should give me negative 7, 2, negative 5, 6, and negative 1, 4. So I'll plot those points, graph those lines, and that is my rotated figure. That's my image. All right, next example, I'm going to do the same thing. This time I want a 180-degree rotation. So we know that rule is negative x, negative y. So everything's just going to change its signs. So a negative 1 and a negative 3 become positive 1 and positive 3. A negative 1 and a positive 1 become positive 1 and negative 1. Then we have negative 1, negative 2, and negative 4, positive 2. So this is going to go a little bit over our old picture, and that's okay. Negative 1, negative 2, negative 4, 2. Q prime and P prime. All right, and that would be our image after a 180-degree rotation about the origin. So you're actually going to try the next two. All right, pause it, and when you're ready to see the answers, hit play. All right, let's check our answers here. For the first one, the rule was y, negative x. So we got the points 6, 1, 8, 0, 5, negative 6, and 3, negative 5. And for the second one, 180 was negative x, negative y. So we got the points negative 3, 2, negative 6, negative 1, and negative 5, 7. So all we've talked about so far are our counterclockwise rotations. So let's talk about what happens if the directions said clockwise. So I'm going to kind of adjust this chart. The first column are my degrees counterclockwise. The second column is my rule. And now we're going to find the appropriate degrees clockwise. So if I had gone 90 degrees counterclockwise, and I wanted to figure out the equivalent clockwise rotation, right, what's going to get me to the same ending position from the same starting position? That was 1, 2, 3 turns, or 270 degrees. So the equivalent to 90 counterclockwise would be 270 clockwise. If I wanted to look at 180, so if I had gone 180 degrees counterclockwise, then I would go also 180 clockwise. And then if I wanted to go 270 counterclockwise, that would be the same as just 90 degrees clockwise. So notice, because a circle adds to 360, each of our equivalent rotations also add to 360. So 90s with 270, 180s with 180, and 270s with 90. So what I generally do is if my directions say to perform the rotation 90 degrees clockwise, I'm going to think to myself, what is the equivalent counterclockwise? So that's really 270 counterclockwise. And that rule is y negative x. So I'm going to do y x, change the second sign, switch them first, change the second sign, switch them first, change the second sign. So that gives me 5, -1, 8, -3, and 1, -8. So you're going to try the next one, pause, and when you're ready to see the answer, hit play. All right, so for our check-in, a 270-degree clockwise rotation is 90 degrees counterclockwise. That rules -yx. So we get the points -2, -7, -6, -5, -8, -1, and -4, -3. So the last thing we'll talk about today is rotational symmetry. And that's when a figure can be mapped onto itself by a rotation between 0 degrees and 360 degrees about the center of the figure, called the center of symmetry. The angle of rotation, which is sometimes called the magnitude, but we'll stick with angle, is the smallest angle through which a figure can be rotated so that it maps onto itself. The angle of rotation has to be less than 360 degrees, or the figure does not have rotational symmetry. The number of times a figure maps onto itself as it's rotating to 360 degrees is called its order. And if you divide 360 by the order, it will give you the angle of rotation. So 360 divided by the order equals the angle that we are looking for. And since we have to have a number less than 360 for the angle, that means the order cannot be 1. The order has to be 2 or greater if the figure will have rotational symmetry. So for these problems, I would I'm going to trace this out, and I'm going to look all the times that my figure, as it rotates, looks like the one that originally was there. So if I start rotating, right, that doesn't look like my original picture yet. It's kind of backwards in my original picture. But oh, right there, it's the original picture. So that's 1 time so far, and I'm not back in my original position yet. So I'm going to keep turning, I'm going to keep turning, I'm going to keep turning, and now it's back to its original position. So that means twice within that time, it looks the same. So the order is the same. And the angle would be 360 divided by 2, which is 180 degrees. Also, this picture had 2 congruent pointy parts that were exactly equally spaced. So that's how we end up with an order of 2. If we look at our next one, all right, obviously not perfect, but we're just looking for it to look like this picture. So already I see it looks like it once. Continue turning, it looks like it twice. Continue turning, that's now a 3rd time, a 4th time, and the 5th time is what gets it back home. So that means there's an order of 5. And if I look at this, I had 1, 2, 3, 4, 5 equally spaced parts of my figure. So my angle will be 360 over 5, or 72 degrees. My last one, I retrace this one. That was actually pretty good. So I'm going to start turning it. Doesn't look the same. Doesn't look the same. Still doesn't look the same, even though when we get to 180. So that tells me I'm not going to have any. There's no way I could turn this picture and make it look like it started. So this has no rotational symmetry. And I could tell that also by looking at it, because these 3 angles are not congruent to each other. They're all different, so it doesn't have any congruent equally spaced parts. So you go ahead and try the last 2. Pause. When you're ready to see the answer, hit play. All right, so in our first one, we see we have 3 equally spaced parts. So the order is 3, and 360 divided by 3 is 120 degrees. For the second one, we see we have 8 equally spaced parts. So the order is 8, and then 360 divided by 8 is 45 degrees. So that is everything we need to know about rotations and rotational symmetry.